Hi, everybody. It's great to be presenting here today. And Eric gave you the title. I'd like to acknowledge the co-lead, Stephen Fry, who's listed on this slide. And we'll move right into it. So obviously, this is a national project, continental scale Canada in scope. So it's not going to be done by two people. So here's the team. It's multidisciplinary, multi-institutional, derived from the private sector, Quante, the Government of Canada, including NRCan, Ag Canada, Environment Canada, and academia, the University of Waterloo and University of Toronto. And as we know from the popular press, groundwater and water resources in general are a topical theme at the moment. And being able to address the water cycle in Canada's water budget at a national level is of paramount importance to the federal government in terms of understanding and managing climate change adaptation or mitigation. And just to highlight a little further the use of groundwater in the context for Canada1Water, then about 30% of Canadians rely on groundwater for potable water, and that climbs to 60% in rural Canada. And the map on the left just highlights municipalities in the black dots that rely on groundwater across the country. This is from Rivera 2014. And it's always useful when other people reinforce your own perspectives. So why do we need Canada1Water? And the two bullets on the right-hand side are quotes taken from a document, Water Security for Canadians, prepared by Global Water Futures as part of the process for the Canadian Water Agency. So I think that there's no argument really about the need for the nature of modeling that C1W is undertaking. Now, it's not the first time that people have approached continental scale modeling in Canada, and there's a variety of approaches that have been employed using Earth observation data, land surface modeling, modeling of surface water through different approaches, and integrated modeling, and that can mean a number of different things. And then physically based. So there is actually a hydrogeosphere model for all of Canada, but most of these models are either incomplete in some regard, or coarse in scale, or don't actually address key aspects of groundwater surface water dynamics. So the objective of Canada1Water then is fairly casual. It's to model the entire water cycle. So atmospheric processes is as a boundary input condition to groundwater surface water understanding. It's to develop that in an integrated groundwater surface water model, and then to evaluate potential influences of climate change on water resources. And we'll get to scale later in the talk. And then to translate that numeric analysis of the system into something that's relevant for non-science communication, ideally for decision makers in Canadian communities. And the project is 3 years. It started in April of 2021. The blue arrow highlights where we are in the timeline, and it will finish in March 2024. So we're well into the data assembly and just starting to spin up the model in terms of the time frame. And look forward to presenting where we are next year, where we should be just entering into the model results part of the process. So this diagram just highlights the scope of Canada1Water, the collaborative nature of the project. A major pillar of funding for Canada1Water is Defence Research Development Canada and the Canadian Safety and Security Program. And the formal title under DRDC is listed there, Evaluating Climate Change Impacts to Groundwater Surface Water. It's also co-funded by Agriculture Canada and the Geological Survey of Canada. And the pie diagram in the right corner, lower right corner, just highlights the nature of funding from the different organizations normalized. So we use the first year of DRDC funding as the standard. They've increased their funding subsequently. The GSC currently funds it to 96% matching funds of DRDC, and likewise for the other elements in the pie. I just lost the screen. There we go. So how are we going to model the complete water cycle water budget? And that's being completed in three modeling elements: the regional climate modeling, land surface modeling, and groundwater surface water modeling. Each of those take place in different pieces of software. They pertain to different parts of the process and system and draw upon radically different data sets and physical processes. So the regional climate modeling is being done in the Weather Research Forecast Model, WRF, and a few of the aspects of the resolution and the time frame are listed here. Land surface modeling is being completed in the community land model and is really looking at near surface processes, soil moisture, soil temperature, permafrost aspects in northern Canada. And then the core element of groundwater surface water modeling is taking place in hydrogeosphere, which is a Canadian developed, integrated, physically based modeling software from the University of Waterloo that is now managed and developed in the private sector by Aquante. So the original concept was to build one model for all of Canada, but it was quickly decided that it would be advantageous to actually dice up Canada into a number of domains based on physiographic and climatic conditions. So we settled on 7 large watersheds. And they're highlighted on the left there, 6 for continental Canada and 1 for Baffin Island. That was a more recent development, as it was originally considered as part of the Arctic domain, but the very unique conditions and isolation of Baffin Island and the size made it worthy of separation. And for each of these 7 model domains, then the diagram on the right just illustrates a number of the data layers that will support the numeric modeling enterprise. So starting in the lower left, you can trace it through sort of up and down along the arrowed line there, the succession of data sets, the hydrogeological domains, the stream network, lake bathymetry, elevation data, and then the discretization and this hydrostratigraphy, soils, geology, and land cover, and then into various climate data sets. A major challenge, sorry, I probably could have had a slightly better sequence of slides, is obviously building all of these data sets at a national scale. So we'll touch in the next couple of slides on some of the elements, and just to acknowledge the depth and breadth of work that's taking place from a climate modeling perspective. This graphic just highlights the multidisciplinary and institutional collaboration here. Regional climate projections out of the U of T, historic climate observations from the Canadian Forestry Service, and then land surface modeling from the University of Waterloo with Chris Fletcher. And a little bit more of a drill down from the climate modeling perspective. We touched on the fact that we're building regional climate models, and a major initiative is going into the integration of lake bodies, open water bodies, particularly the Great Lakes of Canada, which form a crescent-shaped distribution along the edge of the Canadian Shield and have fairly significant impacts on both precipitation and temperature in the lake regions. And there's a variety of different lake models that are being explored to try and optimize the input of the lake effects into the climate modeling. So data assembly challenges, obviously, the fact that we're modeling 1 million square kilometers of the United States in the transboundary watershed region is part of that data harmonization challenge. Then integrating various data sets across provincial and territorial boundaries, along with national data sets. Data normalization, we often have data sets that you could say are like fruit, but they contain apples and oranges. And how do you actually make them a whole? And then classification and parameterization. And just two examples or two cartoons here in terms of those aspects. One good example is the need to classify stream networks nationally, which currently is only available as a sort of heterogeneous classification scheme in some provinces and not others. So just one example then is the digital elevation model, the topographic surface of Canada. DEMs generally provide a flat waterplane surface for lakes. And for numeric modeling of groundwaters, we wanted to incorporate lake depth for lakes greater than 10 square kilometers. So that required a fair bit of data mining and integration and the use of both navigational or bathymetric data from institutions like NOAA or CHS, and also calculation or estimating lake depths for smaller lakes. Then there was integration of marine bathymetric data to 50 kilometers offshore. And then the seamless integration with the various DEMs, and there were two DEM products brought together here, the Arctic DEM at 2 meters and the derived SRTM data managed by the Canadian government at 30 meters for southern Canada, south of 60. And then the removal of peripheral land masses along the coastline that were too small to be integrated in modeling. So model development or data set development is consumed a fair bit of resources and time. So we're going to be discretizing the country in two iterations, basically a coarse resolution model at the scale of fifth order Strahler order streams. So approximately 1 kilometer segment lengths along streams, and the middle diagram just highlights what that would look like for the Nelson River watershed and the number of nodes, and then a finer resolution once we iron out computational bugs in the mesh at fourth Strahler order streams, and reducing the length scales to about a 250 meters to half a kilometer along those fourth order streams. So here we have the data conceptualization, integration, and data set accumulation in the top left. The conversion of those data sets into a 3D model, and then the discretization and the spin up in HGS on the right-hand side. So we are currently in the spin up of fifth order streams. And just to highlight that, as a federal government agency, we're interested and concerned about international issues of transboundary water. And the diagram on the right highlights the watersheds at fourth order that we will be incorporating into the model. And we also will be completing a collaborative case study for the Rainy River watershed with IJC and USGS in terms of cumulative effects and the issues that may arise through resource development. So who are the users or potential clients and interest groups that we're targeting? DRDC was clear in their call for proposals that we needed to be able to address community decision makers, and we interpret communities as being quite diverse in character, social, cultural, geographic, economic, and I'm probably running out of time, so I won't go into any of the details here. And this will be achieved through the delivery of data through the Groundwater Information Network, which Eric talked about earlier, and also through the Quante web portal. They currently have a forecasting platform that we will retool to serve up the predictive information from Canada1Water. All of the data sets that we've worked on, where possible, will be released back into the public domain, and that will largely take place through the Groundwater Information Network. So engagement, we're trying to continue the legacy and the spirit of the National Dialogue on Groundwater and engagement with provinces and conservation authorities, NGOs, and First Nations. And we're happy to make a presentation to any of the provinces who would be interested in more science details of Canada1Water. And we're particularly also always looking for insights and perspectives on how to understand regional groundwater surface water issues in these large model domains. So in summary, we have a 3-year project. We're currently 18 months into it. We're producing a physically based groundwater surface water model for climate change scenarios that would be modeled forward to mid-century and end of century. The model will be a monthly historic transient model with a range of decision support pilot tests for the end of the project to support community decision makers. And there we have it. So just a quick acknowledgement to funders and partners. And if you want more information on this project, you can find it on the Groundwater Geoscience Program YouTube, but also on the Canada1 website. Thank you very much.